Log on, tune in, find out. Another good idea from Cambridge.
Compressed sensing third lecture, and this specific title is Deterministic Approach to CS. Thanks, Emmanuel, again.
Thank you. All right, so just looking at the time on my computer, it says 7 a.m., which means that this morning I probably spoke at 3 a.m. for me. I promoted incoherence. I hope I was not too incoherent. All right, so this morning we saw a very simple theory of, first of all, where we are. We are lecture 3. We're going to discuss a deterministic approach to compressed sensing. Tomorrow I hope to be able to show you some ideas that leads to the proof of the recovery from highly structured measurements such as Fourier. And then, as I said many times already, in the second part of these lectures we'll ease off a little bit on the concepts and start talking a bit more about other things and applications and large-scale optimization. Okay, so this morning we talked about a probabilistic theory of compressed sensing, which is very simple to state because all you need is you say that you're randomly sampling sensing vectors that are incoherent. That's all you need. You need nothing more, nothing less. And so in that sense, it's very, very simple. What we're going to do today is we're going to introduce a deterministic theory. It's not completely deterministic, but I'll try to make clear in what way it is. And then we'll see where it takes us. So the agenda for today is we're going to talk about the restricted isometry property, RIP for short. We're going to state a very general signal recovery theorem once the RIP holds. We're going to see examples of measurements obeying the RIP. That's where probability comes back in the theories. It's to get matrices that obey these restricted isometry properties. At the moment, the only technology we seem to have is to use randomness again. But what's nice about this thing is that it decouples the deterministic part from the probabilistic part. Then we're going to try to explain that these results, in what way are these results optimal, and then I would like to discuss the work of some other people and some extensions. Okay, so we're going to talk about restricted isometries and sparse signal recovery, and the concept of restricted isometry cannot be simpler. So we're going to really build two theories of compressed sensing, one which is based on incoherence, which is simple, and the other is based on this concept, which is, I believe, equally simple. Okay, so we're going to introduce numbers, delta k, and these numbers are the smallest scalar such that when I take a vector which is k sparse, that is has k non-zero coefficients, and I hit it with a compressed sensing matrix A, and I look at the squared norm, then I want this vector to have a norm which is between 1 minus delta k times the norm squared of x and 1 plus delta k times the squared norm of x. Right? So that's the definition of the restricted isometry constant. It's the smallest number you can find, such that essentially A acts almost like an isometry on sparse inputs. Right? Okay. Okay, so this is a definition of, it's just a definition, it's not a property, it's just a definition. We call delta k the smallest number so that this property is true. Okay, so of course A is always our big fat matrix, so A cannot act as an isometry on arbitrary vector because A has a huge null space, so there are many x's for which Ax will be 0, for which I cannot have a lower bound of this kind, of course, since A has a huge null space. And so A cannot be an isometry, of course, it cannot be close to an isometry because, well, the columns of A, I have many more columns than rows, so there's no way I can maintain orthogonality. But if we assume that delta k is not too large in this inequality, then what this means is as long as I restrict myself to sparse inputs, that is, as long as I'm going to select a few columns of A, k of them, then if x is sparse, that is, that Ax is a linear combination of a few columns of A, then I want to preserve the norm. Okay, so another way to say this is that whenever I extract k columns of A, another way of phrasing the restricted isometry properties is when I extract columns of A, k of them, I want the submatrix to be well conditioned. Okay, And in fact, the condition number, you can read it off. It's 1 plus delta k divided by 1 minus delta k. Okay? So when delta k is not too large, what it says is that essentially a lot of submatrices of A corresponding to subsets of k columns are well conditioned. Okay? Another way to say the same thing geometrically is to say that if I take the columns of A and I start to represent them in space, maybe they're not orthogonal, they can't be orthogonal, but they're not too far from orthogonal. Okay? That's another way of stating these things. So the restricted isometry constant is simply, by definition, the smallest number delta k such that this property holds. All right. And we'll see that this property and this property alone essentially gives us everything. Okay, so now we're going to go back in the setting that we've seen this morning, where we observe b equals ax, and we minimize L1, so this we've seen. This morning we introduced the notion of best S-sparse approximation of x, which is what we would get if we had an oracle that was telling us exactly which are the S largest coefficient of x so that I could go out and measure them. And we would just see ax, and we would like to try to do as well as this oracle. Okay, so this we've discussed this morning in the context of having rows randomly sampled from a general distribution F. And the result is of the same flavor as what we've seen this morning, and it's very simple to state. If the restricted isometry constant delta 2s is less than square root 2 minus 1, which is roughly 0.414, then L1 recovery works very, very well. And how well does it work? Well, for example, the distance in L1 between the recovered signal and the truth is within a constant of the distance between the recovered and its best S-sparse approximation. Right? So if you're interested in squared error norm, then you've got something like this. You got the distance between x hat and x in L2 is less than the distance between x and xs in L1 divided by square root of s. Right? This is essentially a result we obtained with Justin and Terence in 05. The presentation you see here is a small improvement, and today we know that the same theorem is true if delta 2s is actually 0.5465. There's an upper limit. Delta 2s cannot get too large. All right, so the theorem is extraordinarily simply stated. If I'm lucky enough to have a matrix that obeys this restricted isometry property, then I can essentially recover the signal very well. For example, if the signal were sparse, the error would be 0, and that's why I call this a deterministic result or deterministic series. There's nothing random about this result whatsoever. Okay, so there's a significant difference with what we've seen this morning. There's no probability involved. It's not that with high probability something good occurs. It's just something good occurs. And the second is that it's universal. That is, this holds for all x whatsoever. And I'm going to comment on this at the end of the lecture, but this morning we were fixing x, randomly sampling A, and saying that, well, we would do well. No matter how you pick x, once you pick x and I randomly sample A, I do well. This says that you take an A and you do well always. Okay. So it's deterministic. There's nothing random about this. It's universal. It applies to all x. And I think every undergrad can understand what this result says. All right. Okay, so of course, if x happened to be S-sparse, then the recovery error is 0. So that's what we've seen this morning. The error is 0. And of course, what would be wonderful is if I could find a matrix so that the number of measurements I make is so close to S that with very few measurements, maybe with 3S measurements, I get what I would get if I had an oracle telling me exactly where to look for information. Okay, so it's going to be a powerful theorem if I can find a way to construct matrices for which S is very close to M, right? For which delta 2S less than 0.414 is close to an S for which this holds is close to M. Okay, so that's a result. That's kind of the only real results we're going to discuss today, and we're going to discuss it in detail. Okay, so the first thing so this is a universal result, and we need to talk about universality a little bit. And so one can ask, when does sparse recovery make sense anyway? Okay, so we have an underdetermined system of equations to solve. I may tell you that the solution is sparse, so that you know that the number of non-zero coefficients in the right-hand side is at most s. Is there enough information in B to actually recover x, knowing that you know that the right-hand side is sparse? Well, of course, for this to be able to do something intelligent, then of course, if the null space of A contains sparse vectors, that would be a bad thing. So perhaps it's not going to be possible for all A's, but maybe it's going to be possible if the sparse vectors lie away from the null space of A. Right? Because of course, if I have sparse vectors in the null space of A, well, there's nothing I can do. Okay. So what you can do and what you can prove and what anybody can see that, yes, it is possible if you have an algebraic property about this matrix A, which is very simple, which is that you take any two S columns of A and they must be linearly independent. Right. So if I take two linear columns, two S columns of A, and if they are linearly independent, I claim that if there is an S sparse solution, it is the only one. So if you can find an X which is S sparse, which fits AX equals B, then you can guarantee that there's no other. And why is this? Well, suppose that you've found an S sparse solution, and let's try to find another one. So let's say, REA solved a big problem on his computer. It comes with X1, and I say, well, I know that two S columns of A are linearly independent. I can tell REA that's the only one. And why? Because suppose that there's another one, X2, which is also S sparse. Then, of course, AX1 is equal to AX2. They're both S sparse, and they both reproduce the data. And so I can subtract those two solutions. Okay, so maybe that's the X1, which is the first part, which is my X1, and then it's 0 afterwards. And 0 and minus X2 would be this guy. Okay, so I can subtract them, and so I've got A of X1 minus X2 is going to be 0. But X1 is S sparse, has S non-zero coefficient. X2 has also S non-zero coefficient. So X1 minus X2 has at most two S non-zero coefficients. And so A of X1 minus X2 is 0, but this is a vector, this is a linear combination of two S columns of A at most, maybe less. And I know that every subset of two S columns are linearly independent, so the only way that can happen is if X1 minus X2 is 0, and if X1 equals 0, if X1 equals X2. And so I know that if you give me a matrix that has two S columns of A linearly independent, that if I find an S sparse solution, that's the only one. All the others will be less sparse. A few more, they will be denser, sorry, I'm sorry. That's something that I don't know if people work in error correcting codes, but that's a property that everybody uses in error correction. The coding matrices are matrices such that small subsets of columns are linearly independent. Okay, but there's a converse, and of course in general, if A has two S linearly independent columns, then I won't be able to find a unique solution, right? So for example, if there's a vector which has two S non-zero components and is in the null space of AH, of A, which means that AH equals 0, then I take this vector, which is a vector you see here. It has two S non-zero components. I'm going to pick the first S. I'm going to say that's X1. I'm going to pick the last S components. I'm going to say that's minus X2. And by construction, so H is going to be X1 minus X2. X1 and X2 are both sparse. AH equals 0 means that AX1 equals AX2. And yet X1 and X2 are very different. In fact, they could have disjoint supports. So what we're learning is there's a very clear transition for sparse recovery, which means that if we could solve combinatorially hard problems, and it seems that the picture is completely understood, that if two S columns of A are linearly independent, then I can do stuff, and if they're not, then I can't, at least in a universal sense. Now, what does the restricted isometry say about this? So one other way to state the isometry constant is to break the vector x into and write it as x1 minus x2, essentially, right? So another way to say what the restricted isometry property is to say that for all k-sparse vector x1 and x2, we're going to look at their differences. So we're going to look at x1 minus x2. And just restating what the restricted isometry property says is that the norm of ax1 minus ax2 squared needs to be between 1 minus delta 2k times the norm of x1 minus x2 squared, and 1 plus delta 2k times the norm of x1 minus x2 squared. Okay, so that's another way of expressing the restricted isometry property. And from what we've seen, the lower bound is completely crucial, because if we did not have this lower bound, then I could have sparse vectors in the null space of A, and then I could not do anything. So the positive lower bound is what matters. The upper bound doesn't really matter so much. It matters a bit, but not really. What matters really in this restricted isometry is how far away are sparse vectors from the null space, and the restricted isometry property quantifies this statement. Okay, so this lower bound says that if I have two distinct signals, x1 and x2, which are both sparse, the lower bound says that they cannot be mapped too close, which is very important for signal recovery. It's also very important when we're going to deal with noise. Because if, for example, 1 minus delta 2k could be 10 to the minus 20, then I take two signals, they map by A, they're still distinct, so maybe they're still distinguishable, but then I add noise and everything is lost. Okay? So what it says is that the lower bound says that signals that are far apart cannot be mapped too closely. And of course, there's an analogy with error correcting codes. And of course, if the lower bound does not hold, then we've seen that we could have two sparse vectors such that ax1 equals ax2. All right. So a picture looks something like this. This is a picture from Mike Wakin, a former postdoc. So what it says, the restricted isometry property, is that, of course, this ratio is bounded away from 0 and infinity. And what it says is that if I have sparse vectors, which, of course, sparse vector leaves on coordinate planes, then somehow this mapping, which Mike calls phi, and the other Mike called phi yesterday, which is A for us, is actually preserving the distances. That if you're kind of not if you're not too close, after projection, you maintain the distance, so that you're still distinguishable. All right. Okay, so there's an interesting phenomenon here, which is that suppose that there is an S-sparse solution to AX equals B. What is it that we've learned? We've learned that if delta 2S is less than 1, that's the only one, right? Because then we have our lower bound, and delta 2S less than 1 is equivalent to saying that the columns of A, 2S columns of A are linearly independent, so we know that there's only one solution. And if we have a bit more tightness around 1, if delta 2S is less than 0.456, we know that the solution to the L1 problem is unique and the solution to your L0 problem. So we have a formal equivalence between something that is combinatorially hard, which is to solve the L0 problem subject to Ax equals B, and something which is a linear program, which is to solve an L1 problem under the constraint that Ax equals B. Of course, this equivalence does not go all the way, because if it were to go all the way, then, as we know, you would prove again that P equals NP. So it has to break somewhere, and we know that it breaks at around 0.707, maybe lower. Well, we know that if delta 2S is bigger than 0.7, roughly, the solution to LP may not be the sparsest. Like linear L1 does not give you the L0 solution. In fact, you can see this geometrically, and you can actually calculate the value that will make L1 fail, and it's not difficult. So what you say is, okay, so here's a column of A. So let's say I'm going to give you a column of A, which is this one, which we're going to call A1. And then let's say that we have two other columns, A2 and A3. Okay? And now I send you B equals A1. And then what you could think about is, well, but you know I can make A1 by summing A2 and A3, and because A2 and A3 are a bit bigger than A1, I can take smaller weights. And so on a problem like this, then L1 will fail, because it would prefer to actually make the column A1 by using slightly larger vectors so that their coefficient is smaller. And so L1 will not give you the L0 solution. Okay, so what I want to discuss now are measurements obeying the restricted isometry property. Okay, and that's where probability comes back. So far, it's a deterministic theory, and I want to kind of give you an idea of, so we've seen many measurements this morning, and for all of them, we know that they obey the restricted isometry property, provided that the number of rows is large enough. Okay, so the first example of measurements is a Gaussian measurement where the entries are IID normal 0, 1. And we know that the restricted isometry property for Gaussian matrices holds very, very soon. That is, as soon as the number of measurement is of size sparsity times log of dimension divided by sparsity, then the restricted isometry property holds. Okay, this morning we've seen another type of measurements where now the entries of A are plus or minus 1 with probability 1/2. And for this kind of measurements, the result is the same. The restricted isometry property holds as the number of samples you take is of size sparsity times log of dimension over sparsity. All right. And this kind of results are not really difficult to establish. And so I'll mention how you could get the restricted isometry property for the Gaussian ensemble, for example. What's more difficult is that if you look again, it's always the same in this field, that if you look at structured measurements such as subsample Fourier transform, things become difficult. And for this Fourier transform, we know that the restricted isometry property holds if I take a number of samples which is of size s log n to the 4th. Okay, so it's different from what we see this morning. What we saw this morning, if I get to see s log n for a coefficient of a sparse signal, I can recover it. What this says is if I take s log n to the 4th, I can recover all sparse signals. Okay, and it's unknown whether we can lower this exponent. People have told me that bringing this exponent to 1 is a big deal, because you would prove conjectures in other fields in doing so. In general, if we take the general ensemble that I've discussed this morning, where you sample from a power distribution with this incoherence property, then it's the same as Fourier, except you multiply by the coherence parameter. Okay, so for many random ensembles, we know that the restricted isometry property holds, and so we're in good shape. Okay, and because of what we've discussed before, in the lecture yesterday afternoon, I said, well, if I take S log n over S measurements with a compressed sensing approach, I get an error which is smaller than what I get by simply measuring the S largest measurement. And so the fact that it holds for the Gaussian ensemble, for example, completely justifies this claim, since, well, we know that if I take m measurements, and if m is S log n over S on the order of this, then by the deterministic theorems we've seen, we know with very high probability I will obey the restricted isometry property, and if I obey the restricted isometry property, I have this. Okay, so this is the implication of compressed sensing, that you can do simultaneous compression and acquisition because you take very few samples, and then you recover by L1, and you guaranteed the error we've seen already a few times. Okay, and in practice, except that I don't know if you can see, but in practice, this works well. The oversampling that we need in practice to get to within the distortion we would get by knowing ahead of time the largest coefficient is about 3. So here's an image. It's a real image now, which is not sparse at all. What you're seeing is the recovery I could get if I knew the 6,000 largest wavelet coefficients. And here's the recovery that you get by essentially taking 18,000 coefficients and recovering by L1, or something a bit more complicated than L1 here. We weighted L1, and you've got the same distortion. That is a distance, the error of these two approaches is the same. So measuring everything, throwing away everything but the 6,000 largest coefficients, or taking directly 18,000 Fourier samples and then recovering by this kind of convex business will give you the same distortion. And that has been reported by lots of other researchers as well. Okay, so now what are the proof techniques to prove that various ensembles, measurement ensembles, obey the restricted isometry property? So there are things that are easy and there are things that are complicated. For Gaussian, I would say that this follows largely from very standard tools in random matrix theory. I'm going to review some of these tools, and if I had to isolate a person, I would give the name of Jarque, because there's a very crisp thing that he did that makes the argument very elegant. For the binary case, there was a proof proposed by Baranyuk, Davenport, Devore, and Wakin, but it's really all over. It's all over the literature of geometric functional analysis. For example, if you look at the work of Litvak, Pajot, Ruderson, and Tom Jacques Jagerman, you'll see similar things. And how does this work for the binary case? What you do is you fix a vector x, and you show that for a fixed vector x, ax is almost, the norm of ax is almost equal to its norm. Okay, so the way this proof works is the way, for example, the Baranyuk proofs work is this: like you just fix x, and you prove that ax squared is less than 1 plus delta what you want for a fixed x. But then you prove that this holds with very large probability for fixed x, and then you use a covering argument. Okay, so you take an x, you show that for a given x, I have what I want, and the probability that this inequality holds is so that the probability fails, the chance that this fails is so low that actually you can use a covering argument to kind of extend this property to all sparse vectors. Okay, so that's the way binary works. DFT, as usual, the discrete Fourier transform, is a completely different business. Here you have to use lots of tools, some geometric functional analysis. You can apply Ruderson selection theorem, but that's not sufficient. There are tools such as the non-commutative Kinching inequality that play a big role. You're going to have to calculate entropies. You're going to have to use Dudley's method. It's a very different business. Okay, so with Terence Tao, we proved the restricted isometry property for Fourier with, I think, log n to the 6th. And then Mark Ruderson and Roman Vershinin were able to, using better tools, lower the exponent a bit to what it is known now, which is s log n to the 4th. Now, these tools, they are also another big name associated with the kind of ideas you need to actually bring this to completion, and that's Jean Bourgain. So Jean Bourgain published a very important paper on lambda p sets, and a lot of the techniques that he introduces in his paper are used to actually prove the restricted isometry property for Fourier. And so if you move to Fourier to this incoherent sampling setup, then it's essentially the same as for the DFT, and there's not, once you know how to do it for Fourier, you know how to do it in general, essentially. Okay, so a lot of, that's where compressed sensing overlaps with mathematicians working in geometric functional analysis who have developed an astonishing array of tools to deal with problems of this kind. Okay, so now how would you prove the Gaussian, the restricted isometry property for Gaussian? So here I'm going to be a bit more tutorial. I'm sorry I'm not going to talk to the specialist, but for students maybe there's something good for students to learn on how you would do it for Gaussian. So suppose I have a matrix which is IID and has normal entries with mean 0 and variance 1 over m. What I want to show is that when I take columns of this matrix and I look at A star T, A T, I want to show that the eigenvalues of this matrix are well separated from 0 and infinity. For example, I might want to show that they're between 1/2 and 3/2. Okay, so it's well known in our business that A star A is a Wishart matrix. And so it's a question about eigenvalues of Wishart matrices, which is a topic that has been extensively studied. An equivalent formulation of this is to show that the singular values of your matrix AT are well separated from 0. And so remember that AT is, so I have a fat matrix. I'm going to take a subset of column. That's AT. So what I get to see here is I get to see a tall Gaussian matrix, and I want to understand the distribution of its singular values. Okay, so if I take a matrix which is now n by s, so this matrix is going to be M by S, so it has M rows and S columns. We've known for a long time that actually the eigenvalues, so this matrix I'm going to call X from now. So this matrix, this submatrix I'm going to call X, not to carry AT. So I'm going to call X, so X equals AT. Okay, we've known for a long time that the spectrum of X star X has a deterministic limit. That is, when S and M go to infinity in a fixed ratio, so that the ratio between S and M goes to C, where C is less than 1, so I have a tall matrix, we know that the eigenvalues are going to converge, the spectrum will converge to a distribution which is supported in the interval 1 minus square root of C squared and 1 plus square root of C squared. Okay, and in fact, we know the shape of the distribution. It's a Martian-Kopastor law, and that's something that plays a very important role in asymptotic random matrix theory. We also know that the minimum singular value and the maximum singular value converge almost surely to the edge of the spectrum. So we know that as the dimension grows to infinity, that the minimum singular value will be deterministic in the limit and will converge almost surely to 1 minus square root of C. We also know that the maximum singular value will converge almost surely to 1 plus square root of C. So we have a good chance, because what it says for us, it means that essentially if we believed in asymptotics, that our matrix will be well conditioned, since all of its singular values would be between 1 plus square root of S over M and 1 minus square root of S over M. So I just need to make sure that S is a bit smaller than M, and I would have well conditioning automatically. The problem with these results is that, of course, they're asymptotic in nature, and we don't do asymptotics. So we need really large deviations for finite size, not asymptotic results. Okay? All right. But for finite size, we have actually very precise concentration bound for the top and minimum singular value of a Gaussian matrix, since we know that for finite samples, the probability that the top singular value is actually above this plus a small constant t will actually decay exponentially in M. And we know that the converse is true for the minimum singular value, since we know that the minimum singular value, the probability that it's below 1 minus square root of S over M, which is this thing, minus something else, is also exponentially decaying. And so if we have this, then of course we're going to have something very close to the restricted isometry property. All I have to do now is I have to say that this is going to be true for a fixed subset of columns, and I'm going to have to make sure that it holds uniformly no matter how I pick the columns. But you can see that this probability of failure are so low that probably a union bound will just suffice. So, but for the moment, can I justify that for a random matrix, I have concentration around the singular values, like this? Okay, and so can we justify this? And one inequality that everybody that in the field finds extremely useful is the Borel's inequality. And what does this equality say? It says that if I have X, which is an n-dimensional vector of centered unit variance independent Gaussian variables, right? So I have an array of variables xij. They are all independent, normal 0, 1. And if I have a function which is Lipschitz, and Lipschitz means that the distance between f of x and f of y is less than the Lipschitz constant of f times the distance between x and y, then we know that for all t, the probability that this function applied to my array of Gaussian random variables x minus its expectation, the probability that this difference is greater than t is going to be less than exponential minus t squared divided by 2 times the Lipschitz constant. That's what one instance of concentration of measure. Right, that says that in high dimensions, a function f of x does not deviate very much from its expectation. All right. So, but now we're in good shape. We're in good shape because, well, I'm going to have my matrix X, which is, I'm going to normalize it slightly differently to be in the setup of the Borel's inequality. So I'm going to suppose that the entries are normal 0, 1, so that the eigenvalues, I want to show concentration around, so I'm going to multiply everything by square root of m, so I want to show concentration of the spectrum around square root of m plus square root of s. Okay. So if I have a matrix which is IID m by s, IID normal 0, 1, then it's not a very difficult exercise to realize that the minimum singular value is actually a Lipschitz function of x. And in fact, the distance between sigma mean and x and sigma mean of x prime is less than 1. It's a Lipschitz constant with constant equal to 1, the distance between x and x prime in the Frobenius norm. And the same is true for the maximum singular value. We have exactly, in fact, the whole vector of singular values is Lipschitz 1. All right, so we know that sigma mean and sigma max are Lipschitz with constant 1. So if I could just bound the expected value of sigma mean or sigma max, I would be done, because then I just invoke Borel's inequality, and Borel's gives me concentration. All right. But it is known that the expected value of sigma min is, or if you were to look at it this way, the expected value of a Gaussian random matrix, which is S by M, so that its singular values are ran 1, is greater than this. It's known. And that's where, I mean, I saw this in a paper by Stanislaw Jarek. And it is known that for the maximum singular value, it is also known that the expected value of sigma max is less than square root of m plus square root of s, or with this normalization, that it will be less than 1 plus square root of s over m. Okay. And these inequalities involve like something like Slepian's inequality. Okay, so now we can bound the mean. We have a concentration around the mean, and so we just put the two together, and we just apply Borel, and we say with the normalization, the probability that sigma max is bigger than its expected value, but its expected value is smaller than square root of m plus square root of s. I can replace the expected value by square root of m plus square root of s, plus t is less than exponential minus t squared over 2. I have the same bound for the minimum singular value of a Gaussian random matrix, and so I have concentration around this value. And now, if I just divide x by square root of m, what I've got is I've got exactly this. Okay, so now we know that whenever I take a sub-matrix of a Gaussian matrix, we know that its spectrum will be actually very tight. All right, and now we just need to use a union bound. Okay, so now I want to show that for every subset of columns of size 2s columns, I can bound. So I know that for every subset of size 2s, I've got these inequalities. That's what we've just derived. Now I need to show that it holds universally, no matter how I pick the subset of columns. And what we're going to do is we're going to do it for the sigma max. The sigma mean is exactly the same thing. So of course, the probability that the sigma max of AT is the supremum over all subset T of columns of cardinality at most 2s is bigger than 1 plus square root of 2s over m plus t, while by the union bound is going to be less than the total number of subsets of cardinality less or equal to 2s. But I mean, of course, sigma max is an increasing function of the number of columns, so I can just restrict myself to columns of size 2s columns times the probability that for each of them I'm good, that I fail, sorry, which is exponential minus t squared over 2, which is what we've seen before. Okay, and then I say, well, but how many columns of size 2s are there? Well, it's n choose 2s. I have an expansion for this. I mean, it's essentially exponential 2s log n over 2s. And so from what I see, I can see that if this is greater than this, then I will have the restricted isometry property. And what that means is I need to check m, to take m, which is essentially s log n over s, as we claim. And so there is, of course, a similar calculation for sigma mean, which is exactly the same, and therefore I won't do it. All right, so for Gaussian matrices, we know that we have the restricted isometry property as soon as the number of samples is of size S log n over S. Okay, so now I would like to spend a few minutes discussing optimality and say, can we hope to get better results? All right, so now suppose we specialize the theorems of compressed sensing. And by the way, for Gaussian matrices, David Donahoe got essentially the same results. So for Gaussian matrices, we proved that, not in this form, but something similar. For Gaussian matrices, we proved that, well, the distance between x hat and x in L2 is less than a constant times the distance between x and its best S sparse approximation divided by square root of S, and that holds when S is of size m over log n over m. Okay, and so the question is, can we do better with other measurements and other reconstruction algorithms? So perhaps we don't believe in Gaussian measurements, perhaps we don't believe in this theory of compressed sensing at all, maybe we don't believe in L1, there's a lot of things we can question in here, and so we would like to know whether I could get a better bound with other algorithms. Okay, now I'm going to develop an argument due to, a classical argument that appeared in the paper by David Donahoe showing that it is not possible. Okay, the short answer is no. All right, so we're going to be able to make a statement like this, which holds universally, we're going to have to make an assumption about the signal class we care about. And, well, we've seen that, if we take images and we compute wavelet coefficients, then we've seen that they're going to decay fairly fast. And so when I look at a log-log plot, when I reorder the wavelet coefficient of an image, I see some kind of a power law decay. That is, the coefficients on a, so this is a log scale, and I can see that they decay on the log-log plot. They decay like it gives me a kind of a straight line. What that indicates is that the coefficients decay at a certain rate. And so we're going to just take this model of signal class to explain how the results can be thought as being optimal. Okay, so we're going to take a model of signals which such that when I reorder the entries by decreasing order of magnitude, I see a power law decay. And one way to express this mathematically is to say that the k's largest entry of x decays like k to the power minus 1 over p. So if p is 1, for example, it would say that the coefficients decay like 1 over k, which is what seems to be at least when we take wavelets, if you were to fit a straight line, you would see here that the slope is 1, which is roughly what people observe empirically, that the wavelet coefficients of natural images decay like something like 1 over k. All right. So as a model, we're going to take for signals, which is a model that people use a lot in mathematical signal processing. We're going to talk about LP balls, and we're going to be interested in those vectors which have a p norm bounded by 1. Okay, so essentially to have a power decay 1 over k essentially means up to log factors that you're in the L1 ball. Okay, so we're going to take a model that people use a lot, and the model is I'm going to be concerned with signal x such that their p norm is less than 1. Okay, and the p norm is what you would, it's not a norm because it does not obey the triangular inequality, but when p is less than 1, but it's the sum of xi at the power p, the p's power of the p norm. Just for simplicity, I'm going to focus on p equals 1, but everything applies to p between 2 and 0. Okay, so now let's specialize. Suppose that I know that my vector is in an L1 ball. It's in an L1 ball of radius less than 1. And I'm going to take m Gaussian measurements. I'm just going to plug the numbers in here. Well, x, the distance between x minus xs, I can't really say. I can bound it by 1, but that's about it. And so I just plug s equals m over log n over m. Okay, and so just by using the most naive upper bound on the distance between x and xs, which is 1, I'm going to have that the error that you can get by CS techniques is the square root of log divided by square root of the number of measurements. Okay, so that's the error you get by taking m Gaussian measurement and recovering by L1. All right, so now we're going to have to do a bit of geometry and ask, well, can we do better? And so can we do better? We can cast it like this. Can we hope to take m adaptive or non-adaptive linear measurements? So I make a distinction between adaptive or non-adaptive. Non-adaptive is what we've been doing all along. And adaptive would be that as you get to see the first measurement, you have a chance to actually select A the next time any way you want. And so you get the second data point. So you're learning about the signal. And as you're learning, you have the right to change what you're going to measure next. And you could try to apply the best possible strategy. So the best one can hope from m adaptive or non-adaptive measurement is going to be essentially, so we're going to look at every ways of sensing the vector linearly, so by having y equals f of x. So these are the linear measurements we take. But what I'm saying in f is f can actually, the second row of f can depend on y1, and the third can depend on y1 and y2. Because that's what it means to be adaptive. Right, so you're going to make linear measurements, and then you would want to find any reconstruction algorithm, which we're going to call D, so that x minus your recovery, and your recovery here is dy, is as small as possible. Okay, and we want to kind of have a universal bound, so we're going to be concerned with the supremum over all x in our ball, for example, in the L1 ball. Okay, so here you can take any measurement you want, you can have any recovery algorithm you want, and EM will be essentially how well you can do. This absolute lower bound on how well you can do by being adaptive or non-adaptive. Okay, so once you make some measurements, right, this is what we've seen this morning, once you make some measurements, you know that your unknown object B is x is in the ball, for example, in the L1 ball, but you've made measurements, so you also know that it's on a plane. And so, of course, what you do know is that you know that it's in the ball and in the plane at the same time, so it's on this segment. But besides this, you have no clue of where it could be on this segment. If we had a model for signals where p was, like, say, 1/2, the LP ball would look like this. Of course, this would be more pinched, and you would have less uncertainty. Okay, so at the end of the measurement process, you know that x is on an affine space, you know that x is in your ball, and of course, you're not going to be able to make an error which is smaller than the diameter of the intersection of the ball and the affine space divided by 2. Because the best thing you could do is take the center of this affine space, and the error you're going to make is the radius of this affine space, so the diameter over 2. From geometric consideration, I'm going to say that the situation is going to be worse for you if this affine space is not an affine space but actually goes through the origin. So that it's a linear space, because that's where the radius is largest. So we're going to consider, it suffices to consider linear V. V means that this line that goes through the origin. Okay. So it is known that how well you can do, which is this approximation error EM, is essentially is equivalent to what is known as the Gelfand numbers of a set B. And the Gelfand numbers of a set B is essentially, so you're looking at all subspace of codimension less than M. Okay, so you're looking at all linear spaces of dimension less than M. Okay, so that's your V. And so you are actually going to take the supremum over all vectors in your ball on this subspace, and what you're looking for is you're looking for the space such that the supremum of this projection is minimal. So PV is the orthonormal projection onto the subspace V, and you're trying to find a subspace V such that the orthogonal projection in a subsense is minimum. That's called the Gelfand numbers, and it's known that essentially the numbers we're looking for is more or less the Gelfand numbers. The thing is that people in the literature have studied these Gelfand widths because they play a very important role in nonlinear approximation theory, and we know precisely how they look like, thanks to the seminal work of Kashin, which was later refined by Garnaev and Gluskin. And for the L1 ball, they actually tell us within constant what the Gelfand width of the L1 ball is. And it comes out to be of this type, which is that the Gelfand width of the L1 ball is square within a constant of square root of log n over m plus 1 divided by square root of m. So from the lower bound we see at the top, we see that the minimum error by taking any kind of adaptive measurement and any reconstruction algorithm whatsoever will have to be greater than the Gelfand width. So it will have to be greater than this. But that exact square root log n over m over square root of m is exactly what you get by compressed sensing. Right? So compressed sensing achieves these limits of performance. We know that there is no adaptive sensing mechanism and any reconstruction algorithm whatsoever that could provide you uniformly over the L1 ball an error which is smaller. Okay? So we know that any algorithm will have to be, the error will have to be exactly this, but within a constant, that's what we get by compressed sensing, and so we are at the limit of performance. So now I've developed the story for LP balls, but Foucault, Pajot, Rahout, and Ulrich essentially wrote down the similar story for LP p less than 1 recently, and the Gelfand width, they calculated the value of the Gelfand width for LP balls with p less than 1, which is this. And when you plug the thing, that's what compressed sensing gives you. And so no matter what p is, you're at the limit. So what I find surprising about this is you have something which is a bit naive, which is you take Gaussian random projection, you reconstruct with L1. You don't know p, you don't know anything. You always use the same algorithm regardless of the problem you're working on. And no matter what the signal class is, you're at the limit. Within constant, but you're at the limit. Okay, so there's something which is good about L1 minimization is that the single algorithm is universally good over signal classes. You don't need to know the sparsity or the rate of decay of the coefficients ahead of time. It puts you at the limit of what is information theoretically possible. Of course, we have to understand that this is we belong, this kind of worst case error. If we believe in this type of worst case error, this is the story. All right. And so there was a review article like for the public, so Brian Hayes wrote, and so we should not expect even better methods to come along soon because you're at the limit. Okay, any questions about this? The thing is like the value that we know for the Gelfand widths, the constant that we can get by compressed sensing can be made explicit. We know now for Gaussian measurements, we know very sharp and explicit constant. But I think there are people who are more specialists than I am. Do we know the constant in the Gelfand widths? Business? I don't know. So I would not know, this was considered to be a major achievement to actually get this lower bound and this matching upper bound to within constant. So Kashin did not get exactly this upper term exactly right. That was considered to be a very spectacular achievement. Then they got this, and whether C1 is any good, then I don't know. But that's a good question. Okay. All right, so the message here is that we can't really do better. And what's nice about it is we have a single algorithm, which is you don't need to know the rate of decay of coefficients. It will automatically adapt and give you essentially, in the worst case sense, the best you could hope. All right, so now in the last 5 or 15 minutes, I want to discuss other algorithms and extensions. I want to discuss a bit the work of other people. So I think Mike discussed yesterday that, yes, I've been promoting the use of convex optimization, but there are other algorithms that people use in our field, and some of them are greedy in nature, so some of these algorithms are greedy, and I'm going to introduce an algorithm which is called COSAMP, which is due to Deanna Needle and Joel Trop, and we'll see that some greedy type procedure provide under restricted isometry property conditions surprisingly good answers as well. And so I would like to discuss this work a little bit. The key idea underlying COSAMP is that, and so what I'm trying to convey here is that, of course, there is an immense literature about compressed sensing and the restricted isometry property, and people have done lots of things, and there's no way I can survey it all. What I can just say that people have found the RIP to be fairly useful, and I think I'm going to try to present COSAMP that uses a restricted isometry property to show something that might appear to be unexpected. And what we'll see is that we can get essentially, or maybe we can get the accuracy of L1, but using a completely different set of ideas. And here are what they are. So the key idea starting COSAMP is that if I have a matrix that obeys a restricted isometry property, and I hit the data vector B by A star, then it's reasonable to expect that A star AX should look like X, roughly. Because A star A is kind of orthonormal on the support of X, and if I don't have big interference term, when I look at A star AX, maybe I can guess a bit of the pieces of X. Does it make sense? All right. Okay, so, well, because what is A star AX, right? A star AX so AX is going to be the sum of xi ai, so it's the sum over a sparse set T. Okay, that's AX. And A star AX, so what is A star AX? What is the jth component of A star AX? Is, of course, the inner product between AJ and, maybe I should write it, sum of J. So what is this? It's AI times the sum of xj aj. But it's basically, if say the columns are normalized, it's going to be x, it's going to be 0, so it's going to be something that looks like xi times 1 plus the sum over j different from I of xj ai aj. But you see, these are kind of orthonormal. So, and if I have enough cancellations, I should pretty much see this guy plus some random fluctuations behind caused by the other columns. But if I'm having enough orthogonality, maybe I could actually try to guess what xi is. Of course, this is not true. Okay, but the idea is like when I look at A star x, I'm going to have, and I hit it with a column which is in the support. Then I'm going to get xi plus some stuff, and if things cancel nicely, and if I have enough orthogonality, maybe this is smaller than this. And so maybe I can, by looking at the large coefficients, I can maybe guess what coefficients are going to, what columns are going to be in the support. So this is the basic idea. Okay, so when A obeys the restricted isometry property, A star B should be a good, reveal a bit about the support of X, because the large coefficients are likely to be in the support of X, and maybe I can use these things. And so what COSAMP is doing is going to iteratively select component of A star Y to be in the support, estimate those coefficients, and then prune. Okay, so how does the algorithm work? So first you start with my guess for X is X not equals 0, and then we're going to have a residual vector, just like in conjugate gradient, which is B. And the iteration count is k equals 0. And now I'm going to hit the residual vectors with A star. I'm going to look at the large coefficients of A star times the residual. And I'm going to say, omega is going to be the support of the 2s largest component of A star times the residual. And then I had the support of the previous iteration of xk minus 1. So I'm going to merge the new candidates coordinates with the old ones. So that's what this merging operation is doing. It's taking the support of omega, then it's merging with what we thought was the support at the previous iteration. And so that's our candidate support at iteration k. And now I say, well, then if that's your candidate support, run least squares. That is, find the signal which best fits the data in a least square sense with that support. And that's what this is doing. Right. Zt is going to be, if I believe the support is t, then I just run least squares, and I believe that my candidate signal is zt, which is essentially trying to find the minimum between b and ax, right, subject to x supported on t. I build a candidate support, and then I try to find on that support the best fit. But I'm not going to do this because then the support will keep on increasing, so I need to prune it back. Okay, and so what this does is, okay, now compute this solution, look at the solution and trim the largest entries. Okay, so now reduce everything to compute this solution, keep the largest entries, and that's your new candidate signal. So because if I did not prune, the support size would grow very, very large very quickly. And then update, that's my new candidate signal, update the residuals, and repeat until something happens. And what happens? Let's say repeat until the residual vector gets small. Okay, so it's a kind of very simple algorithm. What you do is you look at the residual, you look at A star R, you try to find which columns might be in your support. You merge these columns with what you had already. You solve a least squares problem with this guess of the support, and then you prune it, and then you keep on doing it. It's a greedy algorithm. And the nice theorem, proven by Deanna Needle and Joel Trupp, is that if we observe B equals AX, and if the restricted isometry constant delta 2s is small, they don't really say how small it is, but I don't think it matters very much. If delta 2s is less than c for some c positive, then costamp really returns a solution which has the good properties that we've seen already. Right? So it gets an error, which is a maximum between a precision, which is something you can tune, and this approximation error, which is 1 over square root of x, x minus x in one sense. So here you have a completely different algorithm, which is not based on convex optimization, which is based on a sequence of greedy approximation. Try to take your best shot each time at what the solution can be, operate in a greedy fashion like this. And under the restricted isometry property, what Deanna and Joel could show is that, well, you get essentially the same error bound. Okay, so the runtime is going to be order L, where L is the complexity of applying A or A star, so it's NM if you have a Gaussian random matrix, but it's N log N if A is Fourier, times the log of the 2 norm of x divided by the precision epsilon, and that's a runtime. And they can also show that this is robust to noise. So it's a very, very little, not little, it's a very, very, very nice result that says that you can get similar results, not by convex optimization, by other types of sensing, of algorithms. Here, via kind of a sophisticated greedy algorithm that gives you the same error bound. All right. In a different direction, I want to mention results by Donahoe and Tanner. We have studied the threshold for which L1 works between the regime in which L1 works. So this is for exact sparse recovery. So now we're going to assume that the signal is exactly sparse. So we're going to assume that x the zero norm of x is less than S. And we're going to assume that the matrix is Gaussian. And Donohoe and Tanner have studied the recovery problem in a regime where the dimension of the signal and the number of measurements go to infinity in a fixed ratio. That is, for us, m over n go to delta. And they also care about sparsity, which is, since m and m is essentially linear in n, then we can have, because it's log n over s, right? So what we've seen is that the number of measurements you need, m, is on the order of s log n over s. But if m is proportional to n, then we can deal with s, which is proportional to n as well, right? So if m is delta n, right? So if m is proportional to n, what this formula tells you, is that we're going to be fine. So another way to say this is that S is m over log n on the order of S over log n over m. Okay, but if m is grow linearly with m, log n over m becomes a constant. And so that says that S can be proportional to the number of measurements. The question is, what is this constant of proportionality? And so what Donohoe and Tanner have done is they've been able to use results from polytope theory to actually characterize two kinds of threshold. A threshold which holds universally for all sparse vectors S, and a threshold that holds weakly, that is, that it works for most x, and most means that you draw a support at random and then you put random amplitudes, and that's the second curve that you see here. So in the case of Gaussian measurements, we kind of know the asymptotic expression of these curves. So we know exactly, in the case of Gaussian data, where this transition occurs. Once you in an asymptotic regime where number of measurements grows linearly with dimension, and when sparsity grows linearly with number of measurements. So we know roughly where this transition occurs, right? And so if you read this graph, it says that if you make half of the measurement, then you can have a sparsity which is something like around here, which is, I don't know, 0.7 times m. Okay, so we have some more precise results for Gaussian matrices in an asymptotic regime. Okay. Now, the last topic I want to discuss in this lecture is what if we do not have an orthobasis for signal recovery? But before I discuss this, do you have questions? Or? Okay. All right. So I think something that troubled me about a few years ago was that somehow compressed sensing works very well. So at the beginning I said, well, you have a basis in which you're going to express sparsity. So you pick your favorite basis and you're going to express sparsity. So you have a basis which we're going to call phi, and we're going to express sparsity in the basis phi. So we're going to write that phi equals phi x. Okay, and then we sense the signal f by taking measurements about f, which is the same as a phi x. Okay? And of course, the whole theory replaces a phi by a new matrix A and tells you conditions under which you can expect good things. Okay, so far so good, and the theory is extremely strong, and we understand a lot. In particular, if phi was an orthobasis and A is a Gaussian matrix, so for example, A is m by n Gaussian, this is an orthobasis, well, A times phi is a Gaussian matrix with IID entries, right, because of the invariance of the Gaussian distribution under rotation. So, there's really nothing that changes. But the problem with this is that people don't work with orthobases. They express sparsity in things that are overcomplete, as I explained yesterday, where people like to combine bases to take advantage of each basis. And so it is not true that people apply in practice express sparsity in a fixed orthobasis. Instead, what they like to do is they like to try to express sparsity in a dictionary D that has many more rows, many more columns than rows. Okay, and if you look at work in image and signal processing, well, people would apply curvelets for images. They would apply time frequency representations, which we heard yesterday about for radar signals. And time frequency representations are not orthobases. People like to apply undecimated wavelet transform, which are massively overcomplete. Suppose you want to kind of extract multi-tone signals from compressive samples. You would want to oversample your Fourier transform because it's not clear that the frequencies would fall on your nice Nyquist grid. People would like to concatenate several bases. So a very natural example of D would be that D is an orthobasis and then a second one, because maybe there are some features that, as we discussed yesterday, that are well expressed in the first basis and others that are well expressed in the second one. So in reality, when you look at the practice is that people use overcomplete representations, and the theory does not say much about this. Okay, so most practitioners use overcomplete representation, that is fat D, and why should it work? Why does it work? Because I think that there is really an obstacle, and the obstacle is that I cannot apply compressed sensing theory to AD. I cannot, because it will not be incoherent, and it will not obey any restricted isometry property that I can think of. So what I mean is that what you cannot do is you cannot just push forward the problem and say, okay, as long as phi is an orthobasis, there's no problem. But as soon as phi becomes overcomplete, then you have a big problem. Because when I replace phi by an overcomplete expansion, then this matrix AD may not obey any of the assumptions we've seen before. For example, it cannot obey RIP. And why is it? Because suppose you give me a time frequency representation and we have two time frequency atoms. They could be highly correlated, because that's the point of oversampling, is that you add redundancy, and so waveforms become overly correlated. So if in here, and which is what happens in practice, if in here we have a column that I'm going to call delta I, we have another column delta J. So for example, two sinusoids are nearby frequencies, for example, such that the inner product between di and dj is large. D cannot obey the restricted isometry property, because suppose two columns of D are the same. Then the problem is gone. If two columns of D are the same, and you send me X selects one column of D and you select the other one, how can I, even if I don't undersample, I cannot distinguish them. But that's what people do in general. People in general use overcomplete representations, and I would argue that if we do this, then because D cannot obey any restricted isometry property, if columns are correlated, when I project them, they're going to be even more correlated. Okay, so there's no way AD can obey the restricted isometry property, and so the recovery of X in general is completely out of reach. Okay, and we can see the big obstacle. The big obstacle is, let's say that this column is equal to this one, so DI is equal to DJ, right? If XI is 1 and X is 0 everywhere else, well, in Xi is 0, Xj is 1, and 0 everywhere else, dx is the same because I'm sending you the same column, so you cannot distinguish them. But that's not what I'm asking you. What I'm asking you is, can you recover f? I don't care about x. So we cannot recover x in general, but we do not need x. What we care about its push forward through the representation. So it doesn't matter that when RA sends me D1, I actually misrepresent it as D2 because its effect on the signal is going to be the same. Or I could actually take a linear combination of D1 and D2. It doesn't matter. As long as I reconstruct the good column, that's all I care about because F is a linear combination of columns of D. Okay, so we do not care about X. And so now we're going to try to recover the signal F by another algorithm, which is also an L1 algorithm, but it's of slightly different flavor. We're going to assume that D is a tight frame, which is what people use in most applications. Tight frame means that F is equal to, so it looks like an orthobasis, but it's not. Right. So it means that D star is the identity. But of course, D can be like this and still be D star identity. It means the singular values of D are either 1 or 0. Okay, so so in other words, you're going to have this if D star D, on the other hand, is a projector. So what it says that D star D is a projector. Okay, so we're going to assume that we play with a tight frame, which would be in curvelets and Gabor frames. All of this is true. And to recover, we're going to minimize the, okay, now we're not going to minimize the L1 norm of X. We're going to try to find an object that fits the data. And when I look at its coefficient sequence in my representation D, it's minimum in an L1 sense. This is something we call L1 analysis. And it's different from what we've seen before. It says that we're going to minimize the L1 norm of the coefficient sequence in your tight frame. Okay, so what I'm going to do is, for example, if D is a curvelet transform, I'm going to try to find an object whose curvelet coefficients are minimum L1 norm. All right, so that's the algorithm. And the surprise is that, no, not the surprise, sorry. The result is that if we do this, then it works well. So if I have an arbitrary tight frame, which looks something like this, and if I sense by Gaussian matrices, so if A is a Gaussian matrix for the moment, and if again I define my best S-sparse approximation, which is the largest coefficient of F in my representation D, then what you can guarantee is that the distance between F hat and F is less than the distance between del star star and F minus its best approximation. Okay, so what this result says is that it's okay to use over complete expansion. There's no problem with it. And what this theorem guarantees, it guarantees that if the signal has a rapidly decaying expansion in your representation, in the sense that this error is small, then your recovery error will be small. Okay, so it's essentially the same result that what we had before, which is that, but now we have an over complete representation. And what we're saying is if you have a signal that decays rapidly in your representation, because maybe like me, you were not smart enough to construct a good orthobasis, all you can construct is a tight frame. Then if your coefficient had a sparse expansion in this tight frame, then you would know that the recovery error is small. Okay. All right, but in fact, the result does not hold for Gaussian matrices. It holds, so showing you some applications. So here are some radar pulses. It's an application in radar where now we have a superposition of radar pulses. And what this plot shows at the top is the input signal in time and frequency without the modulations. Okay, so we have 6 radar pulses, I believe. Okay, 1, 2, 3, 4, 5, 6. And here are the frequency content. We have 1 low frequency, 2 at intermediate frequencies, and 3 at high frequencies. As we can see, these pulses overlap in time, they overlap in frequencies, and so they overlap. And so what we're going to use is we're going to use a time frequency representation and express sparsity in this time frequency representation, which happens to be quite over complete. So D is substantially above N. And when we recover the signal by L1 analysis, we have at the top plot is the recovery in the frequency domain. So I'm sorry, you can't really see the colors. But essentially, we have blue curves and green curves on the log scale. And so we recover the frequency content of these signals rather well. And if you look at the recovery in the time domain, then you recover your 6 radar pulses. You have 3 of them right here. And essentially, the red line is the size of the error. There's an improvement over L1 analysis, which we call reweighted L1, which would really improve things quite a bit in this example. So it says it's a reweighted L1. So you solve an L1 problem, and you solve another one, and that's it. And there you really clean up the frequency spectrum, so you can recover all the frequency content very well. And then you can see that the size of the error is getting very tiny. Right? And so this is using, I mean, at least if you want to understand this recovery methods, we cannot really go through the RIP technology as is because of the overcompleteness. But underlying all of this, there is RIP. And what makes everything works again is RIP. Now, except that you just need to adapt the property you want. And so now you want A to act an isometry not on sparse inputs, but on subsets of S columns of D. So as long as A is an isometry over sparse subsets of columns of D, you'll be fine. And so all I need now is I need that A times V, where V is not a sparse vector, V is D times a sparse vector. If this obeys this restricted isometry property, which is a very natural extension of the restricted isometry property, so if I look at all the union of all subspaces spanned by all subsets of S columns of D, right? So that is for all vectors of the form dx, where x is S sparse, and there's no way I can get A dx to be this. This is not possible because of correlations in the column of D, but that's not what I'm asking. I'm asking this. Holding for all sparse x, and that I can get. Okay, and that's all I need, because if you have a property like this, then if the restricted isometry constant is small enough, then you get this general recovery theorem that says that you can use over complete representations. What you get is you get an error term that looks like this. So if you decay rapidly, the error will be small. Okay, so I discuss this because it allows me to connect to a paper that I really like. And first of all, how would you prove which matrices obeys this more general version of the restricted isometry property? Well, if A is IID, it will do it. And in fact, there's not much that you need to change. If A is a matrix with IID sub-Gaussian entries, what you do is you do what people do for binary. You prove that for a fixed x, you're fine, and then you take a union bound, and you're just fine. So we know that random matrices will obey this more general form of restricted isometry property. That's all the usual measurements will do. What I want to mention is this result that I really like, which is due to Rachel Ward and Felix Kramer, which is a very recent result as well. And I really like the result because of its simplicity and its power to some extent. It says that if A obeys RIP, so suppose I have a matrix that obeys a standard RIP, the standard restricted isometry property that we have seen. And suppose now that I'm going to randomize the signs of the column. So I'm going to multiply each column by a random sign. Then that's it. This matrix obeys DRIP. Then A obeys DRIP with very large probability. So just by randomizing the signs of the columns of a matrix that obeys RIP, I obey DRIP. So I know how to have I'm now a matrix that sorry, it's getting late. I know how to construct a matrix that obeys DRIP and has a fast algorithm, takes a Fourier matrix, randomize its sign, and that's it.
So that's for a tight frame matrix, or?
Yes.
There's some condition.
Yes. I'm not sure, because I think DRIP is just this. I think that's all you know. No, it's not for a tight frame. You don't need a tight frame for that. Okay, so the work of Felix and Rachel overlaps significantly with work that has been going on in a very exciting work led by Nir Aylan from the Technion and Edo Liberty. So we've known in geometric functional analysis, there's this wonderful result called the Johnson-Lindenstrauss embedding theorem. And what the Johnson-Lindenstrauss embedding theorem says essentially that if I take n points in n dimension, if I take n points, so if I take x1 through xn in Rn, then I can find a projection of dimension, so I can find P, a projection of dimension d by n, such that P of x is between 1 plus and minus epsilon of x squared. No, the inner distances, sorry. So that preserves pairwise distances. So let me write it properly. So that P of xi minus xj squared over xi minus xj squared so that the distances after projection are not distorted. And the wonderful result of Johnson and Lindenstrauss is to show that this works as long as d is a constant times epsilon to the minus 2 times log of the dimension. So you can actually find a very low dimensional projection that preserves pairwise distances. Okay, and so in theoretical computer science, it has become, people like this because it means that I can take data sets, and if I'm interested in their nearest neighbors, I can project these data sets and preserve distances. And so it's become interesting to kind of try to find construction that would have this property of preserving pairwise distances but come with fast algorithms. And so the work of Rachel and Felix really overlaps with this effort in computer science to find matrices with fast algorithms that essentially embed points in low dimension by preserving pairwise distances. And so in this line of work, there's very important work by Nir Aylan and Edo Liberty. Okay, so there's great points of contact between these two fabulous papers. Okay, so to summarize what we've seen this morning we had the fixed x, arbitrary, we randomized A, and we showed that the L1 reconstruction for this x is fine. This afternoon, we discussed universality result where we randomize A, and with high probability, L1 recover for all x. And so it highlights the role played by the restricted isometry property. I think in the field, as far as I can tell, a very big open problem is to come up with deterministic matrices that obey, not to resort to randomness to construct these matrices with good restricted isometry constant. It's completely open. I mean, it's not completely open. I mean, people have done work. We know how to do this when the number of samples is square root of n. Bourgain recently wrote a paper with some of his colleagues showing that you could pass square root of n and go to n to the 1/2 plus epsilon, where epsilon is not really specified, I believe, or maybe it is, but I don't remember what it is. But we have no idea how to do it for m linear in n or n over log n or that kind of dimension. Thank you.
Yes, and could you explain the upper bound drift? I think you explained the lower bound drift. And do you have some explanation for the upper bound? I'm quite
The upper bound for the restricted isometry property? Well, I mean, we can see that, I think I draw a picture, right? That suppose the RIP is not upper bounded above. Then you can have vectors that are much bigger than others. But that's a problem because you go back to my picture. The upper bound plays a lesser role than the lower bound, but still you need something like this because suppose I have a unit vector somewhere, and now I don't have an upper bound on RIP. So I could have, I don't know, I could have very long vectors, which are actually quite still orthonormal. So, and then you give me A1, I will never say that it's A1. I will say that it's a linear combination of A2 and A3 because in an L1 sense, it's much cheaper. So that's why you need an upper bound.
in your
example where you used the analysis dictionary. If you instead had used the synthesis dictionary and done classical L1 but in an overdetermined case, do you still get as good results? Or
Yeah, we get the same. Essentially, this it's people. We get some slightly comparable MSEs. When we start reweighting, which is a little trick that we sometimes people play, it improves with analysis. With synthesis, less. So we like analysis because after we apply reweighting, it seems to work better in practice.
you have no result that says why the synthesis case works as well?
No, no, I don't have them. No, it's not that I'm not looking for them, but I don't have them.
Do you have a similar algorithm than the one you presented today, like what's his name, cosine?
Yeah, cosine.
Or the one with the D star F formulation?
Would it work? I don't know about this. I can ask my Deanna is a postdoc with me. I can ask her. She worked on cosine and she worked with me on the analysis. I don't think that it would apply, but who knows? I'm not in position to give you a definite answer.
The complexity of the cosine, I think you said, was called a sort of log S iteration, right?
Something like that, yeah.
Each iteration there requires an inversion of the A star A
Yes.
matrix, doesn't it?
Yes.
That's quite a complex.
Yes. Some of us disagree a bit in this community where people say L1 is expensive, cosine is cheap. And you'll see why I completely don't buy this argument. So, because as you said, I have to solve S linear, I have to solve F's least squares problem, and when S is 50,000, like in an image, that's a lot. Now, if you have RIP, each of these linear least squares problems is very well conditioned. So if you were to use CG, you could get probably very accurate answers in a few CG iterations because of the restricted isometry property. And so you'd have very well conditioned least squares problem that you could solve very effectively by CG. But still, you have to solve a few.
Sorry, here was someone first.
Besides mutual coherence and the IP, are there any other ways to guarantee a good sensing matrix?
Well, I think you're going to, like, I think we've seen enough randomness now, right? So you're going, if I give you a matrix, then what, right? And this, I mean, these are the two broad ways I know on how to give recovery. There are other characterizations, but I don't think they're very informative.
For example, I have read some papers about statistical IP. Do you think it's a good way? Or
Yeah, but then you have to give up, if you use a statistical RIP, then you have to give up on, then you have to switch randomness. So once you start saying, maybe most of the so for those of you who are not following what the gentleman is saying, is that statistical RIP said that when I look at my matrix A and I take subsets of column, most of these subsets I end up with well-conditioned matrices, but not all of them. And so you can show that under some conditions, you can do well, but you have to put randomness somewhere. And where do people put randomness when they prove results like this? On the signal itself. Then you're going to make assumption about the signal has a random support, it has maybe random signs, it maybe has random amplitude, and then you can do something, because what you do is you take this stuff and you transfer it. But it's a different game now, because now you say, you know, the support is random, the signs are random, then you start making questionable assumptions, which is fine. To some people, people are very happy to say that X is a random sequence of random amplitudes. You know, that's some people, but it's a different thing now. You're going to put an enormous amount of randomness on the signal itself to get out of this non-RIP situation. But you can get good results if you believe that signals are random and have random supports and things like that. which experience does not really. And when I take an image and I look at its coefficients on basis and say, are they randomly distributed? I think Mike was making this point in his lecture. Not really. And here, randomness is crucial to have the thing work. Otherwise, if of course I put the signal on the columns on which you have bad conditioning, then things are not going to work your way.
Right. Any other questions? Okay, well, otherwise we thank Emmanuel again.